Thank you for coming today. My name is Myung-gon Kim, and I am the first author from Korea University. I am going to present our work. Let me get started. If a virtual object is too small or too large, manipulating it becomes a difficult task. In this study, we discovered the virtual object sizes that are optimal and convenient for mid-air manipulation. For mid-air manipulation, we implemented a well-known manipulation technique named 6DF method. It mimics interactions with physical objects by supporting 3DF translations and 3DF rotations. Grab navigation enables a user to navigate the virtual space in any direction. The user can move by grabbing an empty space with a single hand and pulling it. Zoom is implemented for some experiment scenarios. When a user grabs an empty space with both hands and stretches it, the scene is scaled up. In contrast, by squeezing the empty space, the scene is scaled down. We conducted 3 experiments. Firstly, pilot study, secondly, main experiment, and finally, additional experiment for verification. Oculus Quest 2 was used for all experiments. All experiments were conducted in this virtual workspace. The virtual workspace is a 30 meters times 30 meters times 30 meters cubical space. In all experiments, the subjects are asked to perform docking tasks between the same scale objects. The green source teapot should be moved to fit to the silver target teapot. In the docking tasks, 8 different scales of the teapot were used. The minimum was 0.01 meters and the maximum was 10 meters. They were heuristically determined. In the docking tasks, target objects are placed in front of the subject. This shows an imaginary cone, the apex of which is in the middle of the shoulders. The apex angle is 120 degrees. The boundary of the cone's base is regularly sampled at 45 degrees intervals to make 8 sample points. A target is placed per sample point. Initially, the target's center is located at a sample point. It is rotated through Euler transform. Each of the Euler angle is either positive 45 degrees or negative 45 degrees so that the targets have 8 distinct orientations in total. The green source object is in front of the subject at the shoulder's height within arm's reach. Unlike target object, the source's orientation is fixed over the docking tasks. The pilot study was made with 5 participants. Each subject performed 16 docking tasks, which were grouped into 2 experiment blocks. In a block, the 8 target objects were distinct in every aspect of size, position, and orientation. This video shows a docking task performed during the pilot study. There exists a finish button beside the subject. If a subject is satisfied with the result of a docking task, the subject can proceed to the next task by touching the button. In each docking task, we measured the completion time consumed until the finish button was touched. Longer completion times were expected for small and large objects, and shorter times were for medium-sized ones. However, the result does not exactly match the expectation. We observed that many subjects consumed unnecessarily longer time to achieve higher precision even after the source was almost fit to the target. This suggested the need for establishing a certain error threshold such that the docking task can be judged to be completed once the error between source and target falls below the threshold. During this experiment, we measured translation and rotation errors. Based on these errors, a threshold was set. Then the completion time is recomputed. That is, as soon as the pose error falls below the threshold, the docking task is judged to be completed. This figure shows the recomputed completion times. The results are largely compatible with our expectations, showing that the threshold is reasonably set. Additional observations can be made. First of all, both docking tasks were completed in 60 seconds. This led us to introduce the time limit for a task in the main experiment. Completion time is set to 60 seconds. Secondly, the statistics differ significantly between 0.01 and 0.05 meters in this figure. This led us to add 3 more scales, 0.02, 0.03, and 0.04 meters in the main experiment. In the main experiment, participants performed docking tasks not only with 6DOF but also with 6DOF-Z. 6DOF-Z means 6DOF augmented with zoom operation. With 6DOF, the optimal object size is identified, which minimizes the completion time. Each docking task was finished either when the source was fit to the target within the tolerance or after 60 seconds passed. In contrast with 6DOF-Z, convenient working sizes are identified, which are selected by the participants. In the main experiment, 33 subjects participated. Based on the results of the pilot test, 3 more scales were added to the 8 scales used for the pilot study. For each method, a subject performed 22 docking tasks, which were grouped into 2 experimental blocks. After watching a tutorial video, the subject had a 10 minutes practice using 3 objects. Then the rubric for the docking tasks was presented. Finally, the subject started the docking tasks by touching the button. This figure shows the completion times for 11 scales in 6DOF. In order to remove outliers, only the data between the first quartile Q1 and the third quartile Q3 are considered in each scale. We need to fit the data between Q1 and Q3 with a function so that its argmean is taken as the optimal value. Before fitting, the data are post-processed. For example, many values for 0.01 and 0.02 meters in 6DOF would be greater than 60 seconds without the time limit. We abandoned such data, Q3 of which reached 60 seconds. The remaining reliable data are plotted in this figure. Note that the completion times are dramatically high for small objects while they are moderately high for large objects. Based on this observation, we selected square of log function to fit the data. The fitted graph is overlaid on the data in this figure. It shows that the argmean in 6DOF is 0.45 meters, where the minimum completion time is 5.28 seconds. We take the argmean as the optimal size in 6DOF. In 6DOF-Z, a subject is allowed to use zoom to obtain the convenient size of the source and target. If a subject takes the given size as sufficiently convenient, however, no zoom operation will be made. We take the convenient size as the object size at the time when a docking task is completed. This figure shows the convenient sizes for each object scale. This figure depicts the statistics of all convenient sizes. We take the data between Q1 and Q3 as the range of convenient sizes. In order to verify the optimal size and the range of convenient sizes identified in the main experiment, we developed a proxy-based metaphor named diorama, in which a proxy of an object is given with the optimal size. Diorama also supports zoom. We hypothesized that providing such a proxy helped users to complete the docking tasks by minimizing the use of zoom operations. As shown in this figure, it is composed of 3 handles and what we name proxy box, in which objects are manipulated. When the user touches the source and then selects it, its proxy appears in proxy box. By grabbing and dragging stick handle, the user translates Proxybox to a more convenient location to work. Then, in order to secure a better view to work, the user rotates Proxybox by grabbing and rotating torus handle. The user considers Proxybox too small and so scales it up by grabbing and pulling crop handle. By doing so, the target in Proxybox is fully visible to the user. Then the user starts the docking task inside Proxybox. This time, the original source is accordingly manipulated. The proxies are not located in the middle of Proxybox. Feeling uncomfortable with that, the user performs grab navigation by grabbing and pulling the empty space of Proxybox so that the proxies are located in the middle. Then, in order to be able to manipulate the source more accurately, the user performs zoom by grabbing and stretching the empty space of Proxybox. Zoom is not available outside Proxybox. Then the user completes the docking task. Suppose that a user judges that the given size of an object is appropriate enough to be manipulated. Then the user is allowed to manipulate it directly without making a proxy. This implies that diorama is not used at all, but the user simply performs 60F. The additional experiment was made 1 week after the main experiment with the same 33 participants of the main experiment. The procedure of the additional experiment was identical to the main experiment. As in the main experiment, 11 scales were used. Each scale was given twice, making a subject perform 22 docking tasks. In total, 726 docking tasks were performed by 33 subjects. Among them, 3 tasks were not completed in 60 seconds. Analysis is made with the remaining 723 tasks. Among them, 633 tasks were performed by using the diorama, whereas 89 tasks were performed without it. Among the tasks completed by using the diorama, zoom was not used in 524 tasks. It was used in 110 tasks only. This fits our hypothesis. Providing the optimal size objects minimized the use of zoom operations. The mean of the completion time for diorama without zoom is 12.73 seconds, whereas it was 18.32 seconds for diorama with zoom. It reveals that there exists significant difference between them in terms of completion time. This shows that manipulating an optimal size proxy is more efficient than using zoom. For diorama with zoom, we measured the convenient sizes. As depicted in figure, Q1 of the data is 0.18 meters and Q3 is 0.26 meters. This paper reported the results of a series of experiments made for investigating the object sizes that are optimal and convenient for mid-air manipulation in immersive virtual environments. We verified the optimal and convenient sizes through an additional experiment based on a new proxy-based method, diorama. We believe that our studies can give a guideline for advanced studies on the size problems for mid-air manipulation. If fast and accurate mid-air manipulation is required, for example, a proxy-based method is suggested where the proxy is given with the optimal size. If speed and accuracy are not a critical issue, however, we would suggest to provide the virtual objects in the range of convenient sizes. Thank you for listening.